So ideally today you won't learn anything new, but we'll learn some more challenging examples of friction. I called this more friction examples. Yesterday we defined friction. We said that friction was equal to mu, which we said was called the, quote, coefficient of friction. It measured how sticky or slippery objects were. Closer to 0 meant really slippery. Closer to 1 meant pretty sticky. Above 1 meant kind of gluey, times the normal force. And for basic questions like yesterday, the normal force was equal to mg, but I'm going to show you how that can change today. Example 1 says this: consider the bench below. Let's make it one of those gym benches that you push across the gym, those wooden ones that are at the back of the gym. You know the ones I'm talking about? And let's say that it's being pulled by student number 1. Let's make it Jordan. So she's pulling it across the gym at a constant speed. What phrase should I underline, which is probably really important? I should notice this is a trigger phrase, because if it's a constant speed, what can you tell me about all the forces? They must be balanced. Okay? Suddenly, student number 2 pushes down on the bench. You know what? Marley comes along and sits on the bench. Marley comes along and sits on the bench. Oh, got another latecomer. Marley sits on the bench, and some of you are smiling when I said that because you've seen that happen. Someone's pushing it along. Okay. So there's an increased downwards force. Suppose Jordan maintains the same force as before. What happens to A, the weight of the bench, B, the normal force on the bench, C, friction, and D, the motion of the bench? That's a good question. You know, I'm going to answer them right here. I'm going to probably put a little part A right there, and I'll answer that. But first of all, I think this is a good job for a free body diagram. I did one on the left here. I had trouble when I was doing the graphics. Normal force and mg on the left, those two arrows should be the same length. And I'm not sure they quite look like they're the same length. I think this arrow should kind of be about that much longer. So initially, everything is balanced, and friction and Jordan's applied force are balanced. You okay with that, Aiden? Make sense? Okay. Now, Marley comes and sits on the bench. What are the forces acting on this bench? Get the obvious one. Gravity. Has gravity changed? No. Is this bench sinking into the ground like quicksand? Is it flying through like Superman? What that really means is in the vertical direction, in the up-down direction, forces must be, I'm looking for where it starts, letter B. Why can't the normal force be the same size as mg?
Because there's extra push.
There's two forces pushing down. Can you see them? The extra push and mg. So the normal force has to cancel out both of them.
So it's drastic.
Okay. If I wanted to be really fussy, I would try and make it the same length as both of those arrows combined. I'm not going to be that fussy. This is why I said to you in my free body diagrams, I do them roughly to scale, but I try and exaggerate so that it's obvious to me which ones are bigger and which ones are smaller. Okay. Okay. So what other force got bigger then? If the normal force got bigger, friction. Why? Oh, because the normal force is used to calculate friction. So I'm going to do friction larger than it was before.
That's so much larger.
Okay. Now let's answer the questions. A said, what happens to the weight? What's another word for weight? No, now. Weight. No, now. And what's another word for weight? On your formula sheet, I gave you a little column, a middle equation. This is important, and people aren't grasping this. When I say the word weight, what am I talking about? Which force? Mg. Did the mass of the bench change?
No.
So did the weight change?
No.
Stayed the same. What happened to the normal force when Marley sat on the bench? Okay, you can write the normal force increased. You know what? I'm going to go Fn increased. My abbrev for increased is an arrow pointing up. Why did friction increase? Friction increased because the normal force increased. Okay. By the way, this is why sometimes you'll see people, if they're driving on snow, they'll try and put some weights in the back or in the front of the car, especially if it's a pickup truck. They'll load a bunch of stuff into the back of the pickup truck. What are they really doing? They're increasing the mg of their pickup truck to increase the normal force because they need more friction. What's going to happen to the motion of the bench then in that free body diagram? How will that bench accelerate? I guess it's going to slow down. Yeah, it's going to accelerate to the left, but since it's moving to the right, we would see that as it's going to slow down and probably come to a stop pretty quickly. But we're talking about the split second after Marley sits on it. So we can say slows, stops. It says, explain your answer using principles of physics. I really did with my free body diagram right there. I would take that as a good proof. Okay? And then we really used Newton's first most of the time. We said either forces are balanced, it's not accelerating, or forces aren't balanced, it's going to accelerate in that direction. So if you wanted to, you could write a little Newton's first, drop the mic, and walk off too. I'm going to get technical because a student asked me this a couple of years ago, but I'm not going to test you on this. If you've ever tried to slide something really heavy, or even the gym benches, you might have noticed that you have to push harder to get it going than you have to push to keep it going. The reason is there's technically two types of mu's, two types of coefficients of friction. There's one that we call static mu. That's when it's at rest, and that's usually a bit larger. And then there's one that we call kinetic mu. Once you get it moving, it's a smaller coefficient of friction. So read along with me. First of all, it says this. There can be friction on an object even when it's at rest, since the hills and valleys will lock up when we apply even a small force to an object. The force of friction on an object at rest is called static friction, because static means not moving or not changing. Ooh, here's a thought puzzle, and we're going to vote. It says this. Suppose we pull on a desk with a force of 2 newtons, and the desk does not move. Which of the following is true? So let me mime this. I'll use Sarah and Alex's desk. Suppose I pull with 2 newtons and the desk does not move. I'm pulling with about 2 newtons. The desk is not moving. Which of the following is true? A, static friction is bigger than 2 newtons. B, static friction is less than 2 newtons. C, static friction B, static friction is 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. So if I pull on that desk with 2 newtons and it does not move, which of the following statements must be true? Once again, we're going to vote. So who says, Mr. Duick, obviously if it's not moving, A, static friction is bigger than 2 newtons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Who says, no, static friction is exactly 2 newtons? Who says static friction is less than 2 newtons?
That makes no sense.
Who says there's no friction?
That's on ice.
Convince me. Spencer. Oh, so if it's not accelerating, the forces must be, I'm looking for a word that starts with letter B. What if friction was bigger? It would be weird. I would tug on it, and when I let go, it would knock Sarah and Alex backwards and somehow ricochet off. Would it not?
That is crazy.
Now, the reason it's tricky is static friction, is only as big as it needs to be. What if I pull with 3 newtons and the desk doesn't move? How big is static friction? Okay, now suppose the biggest that static friction can be is 20 newtons. I've run the numbers. If I'm pulling with 15 newtons, how big is friction?
Bigger than 15.
No, exactly 15. Can't be bigger than 15. If I pull with... No, can't. If I pull with 60 newtons, how big is friction? If I pull with 19.9 newtons, how big is friction?
19.9.
But now I'm going to pull with 20.1. Okay, now I'm pulling with 20.1. The biggest friction can be is 20, and so there was an unbalanced force and it started to accelerate. So static friction is kind of a weird one. It's as big as it needs to be to cancel out your force until it reaches its maximum. And then as soon as it starts to move, kinetic friction kicks in and it was easier to slide. Hey, Spencer, what law did you use to come up with an answer here? Since you said Newton's first, I would let you write that and drop the mic and walk off. If you didn't know that was Newton's first, you would say forces must be balanced because it's not accelerating. You know what? That's too. I would say A equals 0, comma, forces balanced. That's what I would write. Even better yet, I would write A equals 0, therefore forces. Why use a comma when you can use a therefore? It sounds even more impressive. So static friction acts when you have two objects that are at rest relative to each other. Static friction is what keeps a parked car on a hill from sliding down the hill. That's static friction. A block of wood will remain stationary on a sloped table to a certain point. If you increase the height, the incline, it will eventually start to slide, but on a small incline, static friction will keep the wood from sliding down the table. The force to overcome static friction is always greater than the force you needed to balance sliding friction. Sliding friction is called kinetic friction. I wrote here presumably because this is a question we're not quite sure about yet. We don't have a definitive explanation as to why static friction is bigger. We think maybe it's something similar to if you've ever driven on a gravel road with a lot of potholes. If you go really slow, like half a kilometer per hour, you feel every single pothole. But if you go at about maybe 10 kilometers per hour, you kind of skim over some of the potholes and the ride smooths out a little bit. We think maybe something similar is happening with kinetic friction. Once you start to move, those microscopic hills and valleys don't lock up completely because the object doesn't have time to fall completely into the pothole. Maybe, but that's, we're not sure.
How does it, when it locks up, so it just breaks them?
We think you kind of have to break the welds, and it may be that there's some, at that level, molecular attraction going on just through like charges repel and unlike charges attract. Yeah. I know that, and hopefully you've noticed that when I slide something, once I get it moving, I sure don't have to push as hard, but to get it moving, okay? So if we wanted to be completely accurate, typo, I'll have to fix that, accurate, here's what we would say. I'm going to do example 3 with you, but then you can forget it. I'm not going to test you on it. I'm just doing this because a student asked a few years ago. Yeah?
If you threw like a box out of an airplane and then like the air drag was pushing on it, is there technically friction against the air in the box?
Someone asked me this yesterday. You can sort of treat air drag like friction, but it's more complicated because as the object speeds up, air drag gets bigger. As an object speeds up, friction doesn't get bigger or smaller.
The air doesn't.
Okay.
I know, but there's still like part of like charges.
Yeah.
Yeah, I know, but it wouldn't go into the hills and valleys.
So, ready? Back here now. I'm going to do this example with you. I gave you 2 coefficients of friction. If you look close, one says mu s. That stands for mu static. That's the one that I use when the object isn't moving to calculate friction. Once it starts to move, I use mu kinetic, mu k. That's the 0.25. And you'll notice mu k is a bit smaller. It says an object, a 5 kilogram object, sits on a surface with those 2 coefficients of friction. A says determine the force required to move the object. You know what? I think this is a job for a free body diagram. I'm going to do a free body diagram right there. What are the forces acting on this object? Get the obvious one. Which way? What else? Bigger, smaller, or the same size as mg? I think the same size, but in a little bit you're going to see an example where that's not the case. friction, let's assume we're pulling to the right. So let's have friction pointing to the left. And then we have an applied force of some type. This is what we introduced to you yesterday as our generic force. And in part A, here's what I'm going to say. Let's suppose it's just about to accelerate, but it hasn't started accelerating yet. So if it hasn't started accelerating yet, the forces must be, I'm looking for a word that starts with letter B. I think we're saying this, Liam, to get it moving, F applied has to equal friction. Actually, F applied has to be 0.0001 newtons bigger than friction, but that's the cutoff point right there. How do I calculate friction? What was that? Mu times the normal force. So F applied is going to be mu times the normal force. Have we started sliding yet? So I'm going to use the static mu, the one at rest. I don't know the normal force. Oh, but look. I know the force the same size as a normal force. What? So I can say mu static mg, and now I can plug in numbers. How big is mu static? 0.3, m 5, g 9.8. How hard do I have to pull? Let's do it on the next line. How hard do I have to pull to get this to start to accelerate?
14.7.
Give it to me exactly.
Yeah, it's 14.7.
Okay. Really, I can 14.7000000000001. That would be enough to break the welds and start it to accelerate. Okay. So, B. How hard am I pulling in B? What does it say?
10 newtons.
Will it accelerate? So what's the acceleration exactly as a number? 0. So it says the object is pulled with 10 newtons. Find the acceleration. A is 0. Yes? How big is the force of friction? What? Someone said it. It's got to be 10 because it's not accelerating. Friction is only as big as it needs to be. I'm pulling with 10. Friction matches me with 10. It ain't going anywhere. It's not accelerating. There, I didn't use mu times the normal force. I used newtons first to figure out that's how big it's got to be.
I'm confused.
Okay? What's the acceleration? How hard do we have to pull to get it to accelerate, Matt?
14.7.
How hard are we pulling?
10.
So will it accelerate?
No.
So as a number, what's the acceleration?
0.
So the forces must be, I'm looking for that starts with letter B. So if I'm pulling to the right with 10, friction to the left must be 10.
Oh, okay.
What if I pull to the right with 12? Friction to the left is?
12.
Ooh, how hard am I pulling in C?
20.
Will it accelerate now?
Yes.
Okay, now we have to do a full equation. So C, who's winning?
Friction applied.
Force applied? Who's losing? What's that going to equal? MA. Now it wants me to find the force of friction. Isn't the force of friction 14.7? No. Are we moving?
Yes.
Are we accelerating?
Yes.
Someone said, I don't know. Are we accelerating?
Yes.
Because we definitely have an unbalanced force. Okay? So I'll calculate friction now by using kinetic friction times the normal force. The kinetic coefficient of friction, mu k. It's going to be 0.25 times 5 times 9.8, which is what? Which is what? 12.25? We haven't solved this yet. Said find the force of friction. I did that.
Oh.
Now we can find the acceleration. Let's go back to this equation here. How do we get the A by itself? Alex's theorem. Yes? So if you want to, Matt, you can put a comma there saying, I'm calculating friction. And now it's plug and chug. How big is the applied force in part C? 20 minus, how big is friction? 12.25, no longer 14.7, divided by 5. I can do that in my head. 7.75 divided by 5. What's an easy way to divide by 5? Divide by 10 and then double it. So 0.775, double it. 1.625? No, what is it? I might have done it wrong. 1.55. And that's an acceleration, meters per second squared. 12.25 newtons must be friction for part C. Now, having said that, while it is true that there are technically 2 types of coefficients of friction, I'm not going to be that fussy. Whatever mu that I give you in a question, Aiden, you can use for anything. So I think on the next page, I wrote here, to keep the math nice, we're going to treat both types of friction as the same thing. But I did want to let you know, you're not imagining things when you're sliding something and realize, I don't have to push as hard as I did to get it going. It's true, you don't. And it can be calculated. So friction equals mu times the normal force, where mu is what we call the coefficient of friction. And you don't need to distinguish, Jaden, is it a kinetic, mu k, is it a static, mu s? You can use it for both. I'm not going to be that fussy. How do we find the normal force? From the free body diagram. Okay. Example 4 says, find the maximum force of friction between the mass and the ground for the following objects. Matt, did you miss something?
Yeah.
Here you go. Okay. So in example 4, I'm not going to do a full free body diagram. It just wants me to find the force of friction. For example 4, I'm going to use friction equals mu times the normal force. If you want to be fussy, we're technically going to find static mu, but that's okay, static friction, but that's okay. So let's look at example A. We'll do a free body diagram a little bit. What are the forces acting on this? Get the obvious one. What else? So if I'm calculating friction, friction equals mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? So I can say mu mg. In A, friction is going to be 0.35 times 8 times 9.8, which is what? $27.4? Give it to me to all the sig figs. 27.44? Okay. What if I pull with 27.3 newtons? This won't accelerate. What if I pull with 27.45 newtons? That's when it'll start to accelerate. Okay. B. How big is the maximum force of friction here? Well, again, this is a good job for a free body diagram. What are the forces acting on this mass? Get the obvious one. What else? Bigger, smaller, or the same size as mg? I'm going to tell you right now, is there an extra vertical force? Then it's not the same size as mg. I can tell you that. Is it bigger? Why?
Because it has
Okay? So, for part B, friction is mu times the normal force. I don't know the normal force, and I can't exactly say, oh, but look, I know another force the same size as the normal force, but I can say I can figure out the normal force. How? Are we sinking into the ground like quicksand?
No.
Are we flying into like Superman? Then really what you're saying is everything down has to equal everything.
No.
I'm going to turn that into an equation. What's everything down? Two arrows. What are they?
Mg and 55.
Instead of and, what mathematical operation would I write?
Mg plus 55.
Okay, so if I want to calculate the normal force, everything down has to equal what's everything up? And I can calculate the normal force. Or you know what? Wait a minute. I'm going to be lazy. Mu mg plus 55 in brackets there.
Oh,
There's mu times the normal force. Rather than doing it separately, why don't I do it all in one step? I got a good calculator. Hopefully by now you've purchased a decent calculator. You want me to figure out the maximum force of friction for this one? It's going to be 0.35 bracket 8 times 9.8 plus 55, close bracket. I have no problem, by the way, if you crunch the normal force on a separate line, write it down, and then write it here. But I am saying, for what it's worth, if you've got a good calculator, you don't actually need to calculate the normal force separately. You can do this all in one step. So it's going to be 0.35 bracket 8 times 9.8 plus 55. How big is friction now? The maximum force of friction is 46.69. Now, if I pull with 40, how big is friction? 40. If I pull with 42 newtons, how big is friction? 42 newtons. If I pull with 46.68, still not accelerating, but if I pull with 46.70, it'll start to accelerate.
Yeah, that's right. That's right. Tell 'em.
C. Ooh. This is a job for, they still want me to find friction. I'll do a free body diagram. What are the forces acting on this? Get the obvious one. Get the obvious one.
Gravity. Wait, Mr. Dude,
Yep.
can you go after the last one? Never mind.
You okay?
I got it right. I just did put bracket.
Yeah, you got to put, it's mu times the whole normal force. And the whole normal force in that one was 8 times 9.8 plus 55. Okay. What's the next force I'm going to draw? Normal force. Is the normal force going to be bigger, smaller, or the same size as mg? Why smaller? Because someone is lifting up a little bit by 55 newtons. So I'll really exaggerate it. Dunk. There's the normal force. I'm going to need to calculate the normal force. How? Are we sinking into the ground like quicksand? Are we flying into like Superman? What that really means is everything down has to equal everything. What's everything down? Has to equal what's everything up? How would I get the normal force by itself? So the normal force is equal to mg minus 55. And now I can calculate the force of friction. Friction is going to be mu times the normal force. It's going to be mu times mg minus 55. You know what? I'm lucky. I've got a good calculator that lets me backspace. I think all I need to do is change the plus sign to a minus sign, and I'm good to go. And I get 8.19 newtons. In other words, and again, if you've ever tried to slide heavy furniture or anything like that, you may notice if I have to slide something really, really heavy, like say a stove or a dryer, I lift up. And I've reduced the normal force and made friction smaller. If I want to be a meathead I've been pushed down, and I've made the normal force so big that friction is so big that I'm barely accelerating this at all. Or I can sit on the bench when someone's trying to slide across the gym, increasing the normal force, increasing friction. But probably at least once in your life, you're going to need to move a stove or a dryer, and they're awkward enough that you often can't get your arms around them to lift them up completely, but you don't want to scrape your floor, so you just press really hard with your hands. You lift up a little bit, decreasing the normal force, lowering friction, and hopefully now it'll slide okay without scuffing the floor.
I think it's so much more convenient if we're all using 0G. Not good.
Many things would be far trickier. Can you get Jaden? Jaden dropped a bunch of stuff behind you, Parker. Could you help him out? So, look at situation A. If you wanted to get it accelerating to the right, you would need to pull with more than how many newtons? 27.44. If you wanted to get situation B accelerating to the right, you would need to pull with how many newtons?
46.6.
If you wanted to get situation C accelerating to the right, you would need to pull with more than 8.19. And then in real life, you would notice, oh, I don't have to keep pulling quite that hard. I can ease up a tiny bit. But I'm not going to distinguish that on a test. Friction is going to stay constant. Example 5. So here's an example where we can compare two situations. It says, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. You know what? I'm going to draw a line down the middle of the page, kind of like that. A little better than that, Mr. Duke. Okay. And I'm going to do the left-hand one on the left. I'm going to do the right-hand one on the right. And we'll do a little kind of having people jump in on these. I'll call on a few of you. But first of all, how would I start this out, do you think? What might this be a good job for? So on the left, what are the forces acting on this? Get the obvious one. They gave me a picture, so I'll label the picture.
Gravity.
Okay, so on the left, I definitely have mg down. What else?
Normal force.
Bigger, smaller, or the same size as mg?
Same size.
What else? Well, they gave me this 20. I'll call this the applied force, F applied. How do I know there's friction?
There's always friction.
There's not always friction. Sometimes it'll say mu equals 0 or ignore friction, but the fact that they gave me a coefficient of friction, not much. 0.1 is pretty slippery. Not ice slippery, but probably mud slippery. Like, you wouldn't be comfortable walking on it. You'd have to be a little cautious. So which way will friction be pointing? And I'm going to assume that friction is a bit shorter than F applied. I'll know I'm wrong if when I solve for A, I get a negative acceleration, then I pick the wrong winner. And I'll do a quick fix.
Swap.
What about on the right? What are the forces acting on it? Get the obvious one.
Gravity.
What else?
No force.
Bigger, smaller, or the same size as mg?
It's going to be bigger.
It's going to be bigger.
That's equal to 2 forces pushing down.
I'll exaggerate it so it catches my eye. We still have an F applied.
So, are you using the same coefficient of friction
For both. Yep.
That's a bit unclear.
And friction. I'm still kind of assuming that F applied is winning. Friction got bigger on the right, so maybe not. We'll find out. Okay. A says write a vertical force equation. Liam, are we sinking into the ground like quicksand on the left? Are we flying here like Superman? So vertically, the forces must be, I'm looking for a word that starts with letter B. So everything down has to equal everything. What's everything down on the left-hand diagram? What? Read me the force. 2 letters. Yes. What's everything up? So you're telling me the vertical force equation is that? I agree. Liam, what about on the right-hand side? Everything down has to equal everything. What's everything down? There's two things, two arrows. First, just read, don't jump ahead. And, yes, everything down, mg and 15 has to equal everything up. Okay? That's all I'm asking you to do, write a vertical force equation. Manraj, what does B want me to do? Friction is what times what? No, I have never said that. Don't ever say that. I'll go cuckoo for Cocoa Puffs. That's not what I've said. Friction is what times what? Mu times the? That's what we know. I don't know the normal force. Oh, but look. Liam has cleverly given me an equation for the normal force. What can I replace the normal force with? Manraj, my friend. What? Yes, but you have to walk through that. Especially in Physics 12, the normal force will rarely be mg, and the number of times I see kids just go, friction's mu mg. No, it's not. It's mu times the normal force, which in this case is mu mg. Hey, Manraj, what's mu? I don't know. What's mu with you? 0.12? What's m? What's g? Which is what? I can do this in my head. 10 times 9 point is going to be 98. 98 times 0.12 is going to be 9.8 plus 1.96 is going to be 10.8. It's going to be 11.76?
Yeah. Did you forget to plus 15?
No, I'm doing the left-handed one.
Oh, that's right.
That's why I drew a line.
Left side.
Okay. Matt, you know what? Let's do the right side then, Matt. Let's do you and I. This will work. So it wants me to find the force of friction. Friction is what times what? Mu times the? I don't know the normal. Oh, wait a minute. I do. Liam again cleverly gave me an equation. Apparently the normal force is going to be mg plus 15. And it'll either be mg plus something or mg minus something this year. Next year it'll be more complicated. So, Matt, what's mu? I don't know what's mu with you. What is mu? 0.12. M is 10. G is 9.8 plus 15. Do that one in your head, Mr. Oh, maybe I can. It's going to be 96 plus 15. It's going to be 106. It's going to be 100. No. It's going to be 100. 98 plus 15 is going to be 108 plus 5 is going to be 113 times. Yeah, I can do this. It's going to be 11.3 plus 2.26. 13.56?
Yeah, that's correct.
Yes?
That was great.
And again, if you felt like you wanted to calculate the normal force in line A as a number, but it didn't say in part A to calculate, it just said write the equation. So I'm lazy, I just did that. Liz, what does C want me to do? Okay, on the left diagram, who's winning? Who's losing? Equals? What about on the right-hand side, Liz? Who's winning? Who's losing? Equals? Mr. Duke, it's the same equation. Won't we get the same answer?
No,
Why?
because it's different.
What's different?
Friction's different
Why?
because the calculation last time.
Because the normal force is different. This is what I keep saying, and this is why when you said friction is mu mg, no. It's mu times the normal force. You want to change friction, you can either add oil, reducing mu, or add sand, increasing mu. We looked at that yesterday. Or change the normal force, but we can't change gravity. Alex, what does D want me to find? How will I get the A by itself? Will we use your theorem? Cool. I think we can then say A equals F applied minus friction all over M. Yes? In fact, we can even plug in numbers. F applied, how big was F applied, Alex? I've scrolled down, 20? So it's going to be 20 minus 11.76 divided by 10. I can do that in my head. 20 take away 11 is 9. Take away 0.76 is 8.23. 0.823? No, 0.824. Carry a 1, Duke. Because it's an acceleration. D, on the right-hand side. You know what? Again, the same template equation. A is going to be F applied minus friction divided by M, but there's going to be different numbers going in here. F applied is still 20, but here friction is 13.56 divided by 10. 0.644? So there's an example of two situations. The second one, the normal force was not mg. Good free body diagram took care of it though. I'm hoping on that example you didn't learn a thing. Like I'm hoping that was, oh yeah, Duke, that makes sense. That totally ties in with what I've learned already. Not, oh, what witchery are we doing here, Mr. Duke? This is magic and witchcraft. Is that okay? Couple more and we're done. You do not need to memorize this, but whenever I introduce a concept, I like to try and give you an idea of what's really big and what's really small. So here are some common coefficients of friction. Wood on wood has a coefficient of friction about 0.25. Slides okay. Steel on steel doesn't slide great. How do we get steel to slide on steel successfully? What do?
Oil it.
Yep, so when you lubricate it, it goes down to about 0.1. Much better. Rubber on dry asphalt, anywhere from 0.4 to 0.7. It also depends on the temperature. You may have noticed on hot summer days, is pavement stickier or slipperier? Yeah, so there's other factors here as well. Rubber on wet asphalt, what I do want you to notice is when it rains, you lose about half your friction, which means it's going to take you far further to stop, more distance to stop, and more time to stop. So don't drive like a meathead. Oh, and rubber on ice is terrible. This is why it's so tough to drive on ice.
What's the best friction coefficient on ice?
Well, someone said, well, what if you put studs on your tires? So you can also increase force by increasing pressure by reducing surface area, but we don't look at the physics of that. But if you're wondering how do studs in tires work, it's because they compress the force on a smaller area. And so since pressure is force divided by area, the smaller the area, the bigger the force. Nerd trivia. Okay. Steel on ice, about 0.01. Steel on ice really is pretty good. Like ice skates, if you give yourself a push, most of what's slowing you down is air resistance. If you just give yourself a push and coast, most of what's slowing you down is air resistance. These are all approximate, but giving you an idea. Hey, can we have a coefficient of friction bigger than 1?
Glue. Elmer's.
Rubber on glass has a coefficient of friction of about 2. And one place we have a high mu is on dragster tires. Dragster tires have a coefficient of friction of about 2.8. Mr. Duke, wouldn't that slow them down? Let's find out. Shouldn't a tire with so much friction slow the dragster down?
No.
Convince me. Yeah. What does it say to draw? Parker, talk me through it. Here's our dragster. What are the forces acting on it? Get the obvious one. Yep. Yep. Which way will friction point? Can we use words like left or right or forward or backwards? Because when you say this way, I don't know quite what you mean. Which way is the dragster accelerating?
It's accelerating forward.
So which way had there better be an unbalanced force pointing?
Backwards. Forward. Yeah, forward.
Okay. Which force is that?
That's
Because which way are the tires pushing?
back.
And the road is what causes a car not just to come to a stop. Remember the thought puzzle at the beginning?
Yeah.
This is a really tricky one for non-physics people. This is, again, that physics teacher that I was talking to that was teaching physics out of subject. She had her dragster question like this. She had F engine, and she had friction slowing down the dragster. No. That's what makes a dragster go forward. If it was the engine, you could lose the tires, and the dragster would still drive forward.
Have you seen those things take
Okay.
off? They like compress their tires.
Oh, not only that, What do they do just before the race? They do a smoke show to impress the crowd? No. What's stickier, hot melted rubber or cold rubber? They've done the physics, and they know they can also increase friction by increasing mu by doing a smoke show. Okay? Oh, you don't think dragsters have done some serious physics? Oh, heck yeah. Look at how they're designed. Look at their shape. They totally have. They absolutely have.
But the actual drivers, do they do physics?
No, but the engineers that design them sure have. Absolutely. So this is a neat free body diagram. Friction is what makes cars go forwards. Stickier tires give you better acceleration because you have a higher friction force. They're also crazy expensive. You use the tires for 1 or 2 races and they're gone, and they're probably what, $1,500 a pop or more. That's why you need sponsors.
Red Bull.
Example 7. I like example 7. A force of 120 newtons is needed to push a box along a level road at a steady speed. I should underline steady speed. That's probably important. If the force of gravity is 250 newtons, A asks, what's the force of friction between the box and the road? And B asks, what's the coefficient of kinetic friction between the box and the road? Any suggestions on how I might want to start this out? I think so. How do I know? This goes back, somebody, I can't remember who asked me, how do I know when to do a free body diagram? If it says net force, you can skip the free body diagram. But in general, if there's more than one force, and I see friction and gravity here, free body diagram. So let's do it right here. What are the forces acting on this box? Get the obvious one. What else? Oh, and I can even say, you're right, 250. Cool. What else? Bigger, smaller, or the same size as mg? Is there any hint that there's an extra vertical force in this question?
No.
Are we on a level road, not on a hill?
Yes.
Same size. And again, I think I can say, oh, this time I happen to know it's got to be 250 newtons because they gave me the number. That's convenient. 120, I guess that's the applied force. Yes? Why must this diagram be wrong? Why can't this be all? Why can't this be right?
No friction.
How do I know there has to be friction?
Because you're pushing a box along a
What? So is friction going to be bigger, smaller, or the same size as F applied? I'll eyeball it.
Oh, whoa.
It's like a fluff.
And so normally I would say who's winning, who's losing, but steady speed says it's a tie. So I go straight to saying F applied equals friction. And so when A says what is the force, oh, I can tell you how big friction is. It's got to be 120 newtons, right? So here's an example of a question that initially seemed really, really tricky, but I could find friction almost in my head without doing anything after the free body diagram. It's 120 newtons.
Jaw.
What's B asking me to find?
The coefficient of kinetic friction.
Hey, what's mu? I don't know. What's mu with you? Okay.
Yourself.
Well, the only equation that I have that has a mu in it is that one. I'll write it down. What do I want to get by itself? How would I get the mu by itself? So you're telling me mu is friction divided by Fn.
That would make sense, but
And do I know friction? 120 newtons. Do I know the normal force? And can you see it's newtons divided by newtons? The units do cancel. This is why mu has no units. 12 divided by 25. What's a clever way to divide by 25? Times. No, there is. I'm going to do it on a calculator. I'm going to whip out. 0.48?
That's what I got.
what? I got there. Oh, I did it wrong.
Yeah.
Okay. So again, make sure you're trying these on your calculator to get your wrong mistakes out now, not on the test. So there's an example of a question that I think initially seemed really scary, but Jaden kind of fell apart. Yeah. Newtons divided by newtons, gone. Next page. I like example 8, I like example 8, I like example 8. And I think this is the, oh no, we got one more after this. Cool. And a cool video. 540 kilogram dragster's tires accelerated from rest. I would probably mentally underline the word from rest. That's important. To a speed of 48 meters per second in a distance of 64 meters. A says, what's the acceleration of the car? Do you think I'm going to use forces to find the acceleration here? Or can you see just by reading, I'm pretty sure I'm going to use kinematics last unit to find acceleration here. So I'm going to fall back on my method from last unit, A equals question mark. From rest, what's that tell me? What's 0?
Yeah, equals 0.
Okay, what's that 48?
Yeah.
Sorry.
What's that 64?
Distance.
Okay. Technically displacement, but I don't think we're ending up below from where we started. We're ending up forward, so we can be a little casual. Which equation?
Vector.
Yeah, Liam.
Yes.
Get the A by itself, please.
A equals BI
Liam. VF squared drops down like a domino. Then what? Yep. Yep. Get a little nerdy adrenaline rush. Look at what you did. I'm sorry, but I still, to this day, I enjoy being able to rewrite something in my head without writing anything down because it saves me time. So it's going to be 48 squared minus 0 squared all over 2 times 64. 48 squared. Will minus 0 squared change my answer at all? I'm going to leave it, but I'm going to have to put the bottom in brackets. And I get 18 meters. Just about 2 Gs, not quite. Which is about right.
Jeez.
Okay?
Oh no, I did it wrong again. My calculator is
Well,
B. Did you put the bottom in brackets?
I would never do that.
Yeah, but
Never put it in that.
it's been successful this whole time.
Okay. Liam.
It's a calculator.
Sorry, I can't hear. Hang on. What? Guys, I need you to be quiet. What? What? How do you know it's just F equals MA?
And you're hearing that?
Yeah. How do you know it's just F equals MA? What's your trigger word? A what force? And the what force? Straight to F equals MA. Did they give me M? Liam, did they give me the mass? And are you at the point where you just looked for the word kilograms and found the number? Yeah, this is why I told you at the beginning of the year, as much as I hate memorizing stuff, it is worth memorizing units. It really cuts down on your thinking. So 540, and I just calculated A, 18. So 540 times 18. The net force is 9,720 newtons. C. Now it wants me to find the force of friction. You know what? I think maybe now I need a free body diagram. I've got some white space off to the right. I'm going to do my free body diagram right here. What are the forces acting on this dragster? Get the obvious one. What else? Bigger, smaller, or the same size as MG? I think same size. What else? There's no applied force. What force is pushing the dragster forwards? Ah,
There's no fact
friction.
that far.
Okay. See, normally I would say friction equals mu times the normal force. Don't write this down. Why won't friction equals mu times the normal force help me? I haven't told me mu. So I would have thought that as my first approach, and then I would have gone, yeah. So there's my free body diagram. Who's winning?
Friction.
Who's losing? It's a trick question.
No one losing.
So what's my equation?
We're all winners.
Friction equals MA. Wait a minute. What did I find in part B? MA.
Oh my, 9,720.
So friction has to be 9,720 newtons. Got to be.
Wow. That was so
Okay.
tricky. You're tricky.
See how we put it all together?
Tricky little fuck.
Now, what's D asking me to find? Hey, what's mu? I don't know what's mu with you. So now I can go. By the way, this would also be a good Physics 12 question, but in Physics 12, I would only ask you part D, and I would expect you to clue in that you had to walk through part A, part B, and part C on your own. That's one of the big differences in Physics 12 is I'll give you a multi-step question and say, figure out steps on your own. You've learned enough. So anyways, I think for part D, I'm going to go mu equals friction divided by the normal force. I looked at my equation on my green sheet and just got the mu by itself without bothering to rewrite it.
We don't have.
The mu is what they're asking me to find, right?
Ooh.
So, how big is friction?
9,720.
I don't know the normal force. Oh, but look. I do another force the same size as a normal force. So mu is going to be 9,720 divided by 540 times 9.8.
Wow, that's a big number. 1.83673.
The dragster tires, they should be sticky. 1.84?
No. Oh, yes. Sorry.
Units, no units for the coefficient of friction because it's newtons divided by newtons. They cancel out. Yeah,
No brackets, right? Still got the
sorry.
same
What was that?
answer you did.
Hang on, guys. I need you to be quiet. Yeah. But I've done it all on an equal sign, so I might be just do that so the teacher knows that's my answer. So just to give you an idea of how we can combine stuff from last unit and what we're doing now. This is about as tough as I can throw at you. Okay? If you're wondering, Mr. Duke, what would you consider an A plus level question? This. It says this. If the mass below is accelerating to the left, I guess it's slowing down at 1.2 meters per second squared. Find the coefficient of friction. So it wants us to find mu. We're going to get mu by itself eventually. Any suggestions on how I might want to start out?
You might want to find the acceleration.
Any suggestions on how I might want to start out?
I want to find my friction on the normal.
Take one you know.
What might this be a good job for?
Gravity, free body diagram.
Did they give me a picture? Then I'll label the picture. What are the forces acting on this object? Get the obvious one.
G.
Fn bigger, smaller, or the same size as mg?
Smaller.
How do you know?
Because something's lifting up mass.
So I'll really exaggerate it so it catches my eye. What else? Well, we have F applied. What else?
There isn't friction, but we don't know.
Bigger, smaller, or the same size as F applied?
It's gonna be
Bigger.
Why do I know bigger?
Because
it's accelerating to the left.
Ah,
So it'll be pulling it that way. Crazy how the world
Okay.
works.
so it's moving right but accelerating left. We would call that slowing down.
No.
But Newton's laws only tell us accelerations. Who's winning?
Friction.
Friction.
Friction minus effect.
Who's losing? F applied. What's that going to equal?
Isn't
MA.
it?
MA.
Oh, yeah, I'm stupid.
Oh, my
Never mind, never mind,
It's
never
okay.
mind, never mind,
Okay.
never mind.
By the way, if you take Physics 12, you won't learn anything beyond winner minus loser equals MA. We'll just do more and more complicated situations, but I've taught you most of the forces stuff from Physics 12 as well. Friction is what times what?
You.
Mu times the normal force minus 75 equals ma. What am I trying to find? By 75, I just dropped the F applied number in. You could have left it as F applied, but I stuck the number in since they gave it to me. What am I trying to find? So here's the question, boys and girls. How would I get that by itself? First thing I would do, reverse bad maths. I'll do my plussing and minusing first. So I'm going to add 75 to this side. That's going to give me mu times the normal force equals ma plus 75. Do I know m? Do I know a? I don't know the normal force.
Wait, but we know something.
Well, we're going to have to do a little bit of math. So let's do the normal force right over here. It's not mg, right? So, Parker, are we sinking into the ground like quicksand?
No.
Are we flying here like Superman?
No.
Then everything down has to equal everything. So what's everything down? mg has to equal, what's everything up? Two things. Two things.
85
Instead of and, what would I write?
plus.
Normal force plus 85, or 85 plus normal force. I don't care what order you write it. What am I trying to find here in my little mini equation? How would I get the normal force by itself? Is there a negative in front of the normal force? Not swappy dance. How would I move the 85 over? Minus it.
Yeah.
And I'm going to be really lazy. I'm going to see if I can do this all in one step. Shh. So I'm going to say this. Apparently mu is going to be ma plus 75 divided by mg minus 85. I could crunch the normal force on a separate line, but I mean, I can type that into my calculator, I think. What was m? 20. What was a? I've scrolled down. I don't need to take care, I don't need to put a negative in. I took care of that with my winner minus loser. So don't, someone said minus, no, what is a as a magnitude? 1 point something. How do you know? Has that got meters per second squared next to it? Okay, 1.2. Plus 75 on the top, all over, what's m? G? Is this a fraction? Is there more than one thing on the top? Brackets around the top. Is there more than one thing on the bottom? So I would type it, if I didn't have the fancy schmancy fraction button, and I don't, I would go bracket 20 times 1.2 plus 75, close off the top, divided by bracket 20 times 9.8 minus 85, close off the bottom. And although that was a pretty challenging question, I'm hoping, Marley, there wasn't much new there. And I get a mu of 0.892.
I got an answer, but what's simple? I don't know how I got the right answer.
Okay.
Good for you, Parker.
Yeah.
Wow.
What'd you do?
That's great.
I got.
Then I would say, if you don't know how you got the answer, maybe you want to do it my way.
Well, no,
Just
I
saying.
know how I got the answer, but it's like.
Well, no. I'll come look at yours in a second.
Physics
Okay.
isn't about getting the right answer.
Yeah.
I did 99.
Sorry, hang on. Okay. Is it 0.892? Am I right? Okay, let me pause the video for a second. What's your homework? Your homework is going to be every question here as well. But I said I want it to be done by 10:30. It's 10:15, but short video here. If you're in a car and you hit the brakes really, really quickly, which way will which way will your body keep moving?
Forwards.
Okay? Which way are you accelerating? This is why I've said your body is a backwards accelerometer. If you're in a car and you step on the gas, which way will your body move? Backwards, but which way is the car accelerating? There is an object which, when you accelerate forwards, it points forwards in a car. When you accelerate backwards, it points backwards in a car. There is an object that points in the correct direction of acceleration.
Is it a weird
Put your pencils
balloon?
down, look up.
It's a weird balloon, isn't it?
Not a weird balloon, but you have to find
I
out.
think it's a baffling balloon.
You're a baffling balloon.
Oh, it's a baffling balloon. I'm pretty sure.
Hey, it's me, Destin. Welcome back to Smarter Every Day. So today we're in the rocket van, and I've got two little science helpers here, right? Are you wearing your seatbelts?
Yes.
Okay, we're going to do something pretty interesting. Check this out. I've got a pendulum suspended from the top of our family van, and we're just going to drive forward. We're going to accelerate. So if we're going that way, which direction do you think this pendulum should go? What do you think? 3, 2, 1, go.
Yes.
Which way is it going?
My way.
That's right. It's because I'm accelerating, right? Does that make sense to you guys?
Yes, sir.
So that pendulum hanging behaves kind of like what we're used to, the same way we behave. When we accelerate forwards, we actually feel like we're getting pushed backwards. Okay.
Very good. I was hoping it would make sense. So we're going to change it up just a little bit. Okay, so now what I'm going to do is I'm going to replace this pendulum with a balloon. We should see the same thing, right? Let me cut this off. So what we're going to do is we're going to accelerate that way. So we have the mass of the balloon and the acceleration, so that should net in a force, and we'll have to react with this string, right? You guys ready?
Yes, sir.
3, 2, 1, go. Wait a second. What just happened?
And watch when he
Oh,
slows
when I
down.
stop. The balloon goes backwards when I stop.
A helium balloon will point in the correct direction of acceleration. So here's the question. Why?
Because it's lifting up off the ground so that, I don't know, because before it was hanging from the ceiling, but now it's trying to float up to the air. That probably has something to do with it. Ah, that was close though, right?
Yeah. Sorry? No. We have to talk about why a helium balloon floats. A helium balloon doesn't float. A helium balloon wants to move to where the air is less dense. That's really what floating is. It wants to move to where the air is less dense. When you hit the brakes, air in the van sloshes forwards, and the van front has slightly more dense air. The back of the van has slightly less dense air, and so the balloon will, in air quotes, float to the back to where there's less dense air. When you accelerate, the air sloshes to the back of the van. You don't notice it, but it does, making the van back slightly more dense than the van front, and so the balloon will, air quotes, float to the front.
What's happening?
It's doing the same.
3, 2, 1, go.
I heard somebody say the
There
word
it is,
water.
right
Yeah,
at
you
me.
do something similar.
Why is it doing that? You want to know?
Yeah.
I brought something to show you. Remember I told you I was going to bring this jar earlier? Remember that? So it's like this. Imagine this entire van is just like this jar. And all the air inside this van is just like the water in the jar. Does that make sense? So let's imagine that the balloon is this bubble on top. Because the helium in the balloon is lighter than air, right? So that causes it to do what?
Go up.
Go up, that's right. So if I've got this air that's just like it, what happens if I move the jar that way? All that water sloshes to the back. And when that water sloshes back this way, which direction does the bubble go? You see that? So the air bubble moves in the direction of acceleration. Does that make sense? I know you're 5, but I think you can get this. Okay, so I've got my seatbelt on. If I drive forward real fast right now, which direction is the balloon going to go?
Forward.
Why will it go forward?
Because all the air is splashing back.
That's right. Very good. Watch this. Look at that. You see that? So you know what that means, don't you?
Also notice when he's turning, the balloon points towards the center of his turn, because when you're turning, you're accelerating inwards, not outwards.
That means you have more air to breathe than Daddy does when I'm going fast. Did
Technically.
you realize that?
No.
Yeah, that means when I go fast, that means more air sloshes back there to you, and you have more oxygen to breathe. Doesn't it feel good back there? Okay, so now we have the plumb bob right next to the balloon. So if I go forward, they should spread apart, right? Let's check it out. Is it working?
Yeah.
All right. So what?
So you can try that, by the way, if you ever have a helium balloon and you're not the driver, if you can talk your parents or whoever's driving into going to an empty section of the parking lot, You can try this. If you accelerate, the balloon will point forward. If you decelerate, the balloon will point backwards. Here's a thought puzzle for you. On the International Space Station, if you have a helium balloon and you let it go, will it float up?
No.
You got some homework to work on?
Yes, we do.
So there's your thought puzzle to ponder.
Oh.